welcome back. In this video, we run through a quick probability review, emphasizing the terminology we need for naive Bayes. A random variable can be discrete or continuous. The joint probability is the probability of both x and y occurring. In the diagram, we can see that as the overlapping space between x and y. The conditional probability is a probability that one event occurs given that some other event occurred. If we know that y occurs, what's the probability of x? For example, given a positive disease test y, x would be the probability that you actually have the disease. Conditional probability starts with the joint probability and divides it by the probability of y. Some basic rules of probabilities let us compute unknown probabilities from known probabilities. The product rule lets us compute the joint probability if we know the conditional probability of A given B and the probability of B. The sum rule lets us compute the probability of a variable if we know the joint probability of A over all probabilities of B. The chain rule lets us calculate any number of joint variables using conditional probabilities. Two important values, sometimes called moments, are the mean and the variance. The expectation or mean is the first moment. For example, the expected value of a fair die is 3.5. The variance is the second moment. It's the difference between the variable and its mean squared. If we take the square root of the variance, it's the standard deviation. Next, we look at distributions using R. It's important to understand our data in terms of these distributions. First, let's look at a Bernoulli distribution. This models a binary outcome in a single trial. Let mu represent the probability of the positive class. Let's say I'm terrible at shooting baskets, and mu is 0.2, the probability that I shoot and actually make the basket. Notice that one of these terms will disappear based on the binary choice of 0 or 1. So the probability that I miss plugging in x equals 0 gives us an 80% chance, and the probability that I make it, where x equals 1, is a 20% chance. The binomial distribution models a binary outcome over a number of trials n. The binomial distribution of x, where I make k baskets in n trials, has this form, and let's say k equals 20 for 100 trials. Will the outcome of the binomial be 0.2? No, it's not, because there are many ways we can get 20 baskets out of 100 trials. 100 choose 20 to be exact. What's the expected mean of our 100 trials? The expected value will be n times mu, which in our case is 100 times 0.2 is 20. Let's derive these values using R. First, we make a vector of possible values for k, the number of baskets made, which can be from 0 to 100. Then we multiply each k by its probability and add them together. E is 20, as we expect. The plot here shows the expected value at the center with variance calculated as n times mu times 1 minus mu, which is 16 in our example. Now suppose that I got really lucky when I shot my first 3 hoops and made all 3. That gives me a mu of 1. It's unlikely I can keep this probability up over the long haul. In fact, small sample sizes serve poorly as prior estimates of probabilities. Instead of a prior mu, we really need a prior distribution over mu. We want this prior distribution to be a conjugate, a family member, of our binomial distribution. The beta distribution is a good choice. The first term with the gammas serves as a normalizing constant to make sure the total probability integrates to 1. Let's look at the beta distribution for example in R. We use the R beta function to create 100 random beta samples with shape parameters 20 and 80. Then we plot this curve as the black line. Now suppose I take 15 more shots and make 5 of them. This will make parameter A 30 and parameter B 85. This updated curve is shown in red. The par new equal true parameter is used when you want to plot over an existing plot. The beta equation gives us a way to update our model and calculate new probabilities. So far, the distributions we looked at represent binary variables. Next, we look at multinomial variables, variables that can take on more than 2 classes. This formula gives the probability mass function of a multinomial distribution, where k indexes over the number of classes, k, and each of the m sub i's represents the probability of that class. All of the m's will sum to 1. The iris data is an example of a multinomial distribution. There are 3 classes. If we want to put the 150 flowers in the iris data set into 3 boxes or 3 classes, with an even probability of each class, we could use the R multinomial command here. The output gives us 10 vectors left to right because we said n equals 10. Our size is 150 for each column. We get 150 flowers in each column. Values in each row are the number of flowers in that class. The mean values for the 3 rows are 54, 50.1, and 54.9. The Dirichlet distribution is the conjugate prior of the multinomial distribution. The Dirichlet distribution has k parameters, alphas, 1 for each class. So instead of x being 0 or 1, it can take on k values. In this equation, alpha sub 0 is the sum of all alphas. You can think of the Dirichlet distribution as a multinomial factory. Here we ask for 10 distributions with all our alphas equal to 1. The sum of every row, which is a distribution, is 1. The mean of the columns for these 3 examples are 0.2, 0.38, and 0.39. When we ran with 1,000 examples, the means were closer to 0.3 each. All of those previous distributions model qualitative data. What about quantitative data? We can model our quantitative data with a Gaussian distribution, a normal distribution, with this formula here. Its shape is defined by its mean and its variance. The first line in the graph has a mean of 0 and a variance of 1. That's the black line. The blue line has the same mean but a variance of 2, and the orange line has a variance of 0.5. Different means would shift the curves right or left. The variance indicates how sharp or flattened out the curve is. Hopefully, this was a brief review for you of some probability distribution terminology. It's helpful to understand our data in terms of these distributions, and familiarity with these terms will help you read published papers in machine learning conference proceedings. Next, we move on to Bayes' theorem. Bayes' theorem was developed back in the 18th century by Thomas Bayes, a mathematician and minister. Bayes' theorem lets us calculate the probability of y given x by calculating the probability of x given y times the probability of y all over the probability of x. The final result is the posterior. The probability of x given y is the likelihood. The probability of y is the prior, and the denominator is called the marginal. The marginal is just used to scale the posterior to be a probability between 0 and 1. Let's consider this equation in terms of the Titanic data. The probability of survived given the data is the probability of the data given survived, that's the likelihood, times the probability of survived, that's the prior, all divided by the probability of the data, the marginal. We'll look more at this theorem in the next video as we learn how R implements naive Bayes' algorithm.